Okay. Hello, everyone. So, you have homework due today, tonight, at some point in time, but a bunch of people had emailed me asking for extensions for one reason or another. So, homework, what is this? Homework 2? Homework number 2, due Tuesday instead. So, Tuesday at midnight, so 11:59 p.m. I haven't changed it yet, but I'll change it later. So 1 day extension on the homework. Still, office hours will be later today, actually right after class. So office hours right after this lecture. I'll post an announcement immediately after. So like 5 minutes after. It takes me a little bit to set up the things, but anyway. Then yeah, I would scream all lecture, but it's I gotta preserve my beautiful singing voice, so I moonlight in a metal band, so have to I can't disappoint all my fans. I gotta be able to produce those normal metal notes, so they'd be disappointed if I couldn't. But anyway, anyway, we stopped with our discussion of the inverse. So if you have 2 by 2, the answer of what the inverse is easy. So if you have 2 by 2 matrix, A inverse is 1 over AD minus BC times the 2 by 2 matrix. I swap D and A. Right, so I swap the entries along the diagonal and I negate the other entries. So that's how to remember it. So this exists. This expression makes sense so long as AD minus BC is not equal to 0. Now, for the sake of our further writing, I'm going to call that expression AD minus BC the determinant of A. Don't ask where it comes from yet, because we're going to talk about the determinant in the next chapter. That's the entire purpose of the next chapter. But you have encountered the determinant before probably, and this is the determinant of a 2 by 2. The determinant of a matrix that is bigger than a 2 by 2, unfortunately, doesn't have as simple of an expression like this. So this is the one instance where the determinant is easy to find. So for a 2 by 2 matrix, you compute the determinant. If the determinant is non-zero, then this inverse exists. There's a reason for that foreshadowing. So anyway, one more example of this, just because it's all I have room to do right here. So if A is the matrix, say 3, 4, 5, 6, then what would A inverse be? So to even know if there's a point in writing anything else, I compute the determinant first. So this is 3 times 6 minus 4 times 5. So this is 18 minus 20. This is minus 2. So we are good to go here. So determinant is minus 2. So A inverse is 1 over the determinant. So it's 1 over minus 2 times the 2 by 2 matrix. So I swap 3 and 6 here. And then I have minus 4 and minus 5 on the off diagonal. So what does this become? This is, after I multiply this scalar, every entry in the matrix. So this is minus 3, 2, 5 halves, minus 3 halves. And I'm not going to check now, but you can check that this actually is the inverse of A. So if you multiply A times A inverse or A inverse times A, you would get the 2 by 2 identity, right? Okay. All right. No, see, it's good. You thought it was due. You thought it was due later today. So you like worked hard on it. Now you're mostly done. So you shouldn't be too sad about it. So anyway, the significance of the determinant, unfortunately, I can't answer that right now. It would be a long long diversion, which we're going to get into anyway, so I'm going to punt there and leave that until later. The determinant is going to be basically the thing that 100% determines whether or not a matrix is invertible. So that's the spoiler for the determinant, and that is why it's called the determinant, because it determines stuff. Okay, so here's a nice fact that doesn't really require much of a proof. So if A is an n by n invertible, or I should say maybe A is an n by n is invertible, then for every B in Rn, the equation Ax equals B has a unique solution. It has the unique solution. What? What is the unique solution? Well, if A is invertible, it has an inverse. If it has an inverse, I can multiply both sides of this equation by it. And what do I get when I do that? A inverse times B. Okay, so when a matrix is invertible, look at how nice this is. If a matrix is invertible, then not only is Ax equals B consistent for every B in Rn, but also it's always unique. So not only is it consistent, but the solution is always unique. Okay, so an invertible matrix is basically as nice as possible. Okay, so so the proof here is very easy. Here's Ax equals B. Since A is invertible and A inverse exists, then A inverse times Ax is equal to A inverse times B. Notice I can't just throw A inverse on any side here because I'm not allowed to rearrange these things. In fact, multiplying on the right doesn't even make sense, right? Because X is an n by 1 vector, or n by 1 matrix, because it's a vector. So this I can associate here. Notice I didn't change any orders. Okay, and A inverse times A is the identity matrix. So this is the identity matrix times X is A inverse times B. What's the identity matrix times a vector? Well, of course, it's just the vector itself. So this is exactly what you get. Okay, in fact, you can go backwards here. So not only do you have existence, you got uniqueness. So this is it. Okay, you could turn all those arrows into double-headed arrows if you wanted to. Okay. All right, so that's a nice fact. This should tell you that being an invertible matrix is nice. What's some more nice facts about invertible matrices? Later, we're going to have a theorem so long that I'm going to refuse to write it, and I'm going to pull out the book instead, because if we were actually in class, I would bring like hundreds of printouts to the lecture hall and hand them out. But since we're not, I'm not going to do that, obviously. I'm just going to read a giant list. I'm not going to write out the list. It would take me all class. So anyway, theorem has multiple parts. So first, if A is invertible, okay, then A inverse is also invertible. Oh. And if it's invertible, it's got an inverse. What is the inverse of A inverse? Well, it's A. Okay. All right. Secondly, if A and B are both n by n invertible matrices, then so is AB. And what is AB inverse? This is another tricky one. AB inverse is B inverse A inverse. So tricky. Why is it tricky? It reverses the order. To see why this is, it's actually not that big of a deal at all. So here's a proof. If A and B are invertible, then A inverse and B inverse both exist. AB times what is equal to the identity? If I can fill this in, right? If I can fill in this question mark, then I'm done. Okay. So AB times B inverse A inverse. What does this do? Right? This is A B inverse times A inverse. So this is AI A inverse, if you like. Of course, because there's associativity, I don't have to worry about these stupid parentheses. I can do this in any order. I just can't swap the actual order of the matrices, but I can do the operations themselves in any order that they're written, right? So the order of A and B in all these matrices matter, but the order I do the operations, like I can move these parentheses all I want to, as long as I don't move A, B, A inverse, B inverse. So here, this is I times anything on either side is just the same thing. So this is A inverse, so this is just I, right? Note, real quick. So this is an aside, if you like, to show that it's not. So here's an aside. What if you have A times B and you multiply that by A inverse B inverse? What is this equal to? Well, you're done. You're done there. There's nothing else you can do. AB A inverse B inverse is AB A inverse B inverse. There's no simplification I can do. So no further simplification. Now, if simplification, yeah. So if it turns out that, there's something special about these matrices, so I know that, actually A inverse is equal to B inverse or something, right? Then there's something that I could do here. But otherwise, unless you're in a special case, this is it. So in general, this is all you can do. Okay, now I was in the middle of stating a theorem, so that's just an aside. So theorem continued is part 3, which says if A is invertible, then so is A transpose. And A transpose inverse is, what do you think that is? It's A inverse transpose. Wow. Okay. Cool. All right. So we are done. We are done with that. Okay. Now, by induction, I can actually say a couple other things. So number 2 plus induction says that any product of invertible matrices is invertible. And not only is any product of invertible matrices invertible, but their inverse is just that product of all their inverses backwards. Okay. Yekta saying an example of A not being invertible. Here's a really easy one, the zero matrix. So the zero matrix, just literally the matrix with nothing but zeros, that has no inverse. So zero matrix has no inverse. Pick another matrix, and you can have any entries you want. It can be as big as you want, and make, say, one entire column zeros. That's another easy way to do it. Of course, there are matrices that are not invertible, but they have only non-zero entries. That happens too. So here's an example. If A is 1, 1, 2, 2, this is not invertible. So this is not invertible because the determinant of A is 2 minus 2, which is 0. So in the A inverse formula, you'd have 1 over 0, and it doesn't matter what you got here. That's no good. Right? Okay. So that's another example. Yeah, so unfortunately, just glancing at a matrix, you can't tell. You have to do, I mean, here you could have said why for another reason that we'll see later, but in general, I could cook up a matrix that you can't tell just by looking at it. There's something you got to do. Okay, that something is going to be compute the determinant, but we're not going to do that till next chapter. Okay, so a quick definition. That is useful. It is useful not just for what we're going to do. It's going to be useful later as well, because there's a nice way of. So before we move on to finding A inverse, we can keep track of the three elementary row operations So remember what the three elementary row operations were. I could scale a row, I could swap two rows, and I could do row replacement, right? Those were the three operations I could do. So I could do row replacement, I could swap, I could scale a row. Okay. So we can keep track of the three elementary row operations through matrix multiplication. Okay. So here's how. Quick definition. So this is the definition of an elementary matrix. Okay. We actually don't need this stuff right exactly right now, but a lot of the homework problems are going to involve these things, so it's nice to go ahead and define them so you'll know what it's talking about when those come up. So an elementary matrix is one that is obtained from the identity matrix of some size. So this is an elementary matrix of some size, say n by n, is a matrix that's obtained from the identity matrix via a single row operation. Single elementary row operation. Okay, so here's some examples. Okay, so let's say E sub 1. Let's say I took the identity matrix and I did something to it, where that something is reflected here. And let's say E sub 2 is 0, 1, 0, 1, 0, 0, 0, 0, 1, and E sub 3 is 1, 0, 0, 0, 1, 0, 0, 0, 5. Okay. All right. So let's just check. What was this? Why is this an elementary matrix? I took the identity matrix, that is 1, 0, 0, 0, 1, 0, 0, 0, 1. So imagine this is a 0 here. And I did what to it? What did I do to the identity matrix to produce this thing? I did row replacement, where I took the first row, I multiplied by -4 and added it to the third row, right? So this is row replacement. What happened here? Swap. So swapped rows 1 and 2. What about here? I scaled row 3. Right? Okay. So that's how I obtained these three elementary matrices. Now, note, maybe I'll put these here so I can continue on. So there's my three elementary matrices. So note, if A is a 3 by 3 matrix, it's just A, B, C, D, E, F, G, H, I. How is this affected by multiplication by these matrices? Well, E sub 1 times A does what? So just quickly, 1, 0, 0 times this thing. It actually doesn't do anything to the first row. It doesn't do anything to the second row. What does it do to the third row? It would be G minus 4A, H minus 4, H minus 4B, and then lastly I minus 4C. Huh. So it's actually the exact same row replacement. Right. Similarly, what does E2 times A do? If you quickly multiply this out, in the first row is going to be the second row of A. So DEF goes in the first row here, and ABC goes in the second row. And GHI is completely unaffected. So it's row swapping. And if you check E sub 3 of A, oh, let me write it over here. E sub 3 times A, sorry, does nothing to the first two rows. And the last row is multiplied by 5, so it's 5G, 5H, 5I. Okay. So what did we just do? We just described elementary row operations as these matrix multiplications. So the elementary row operations can be thought of as matrix multiplications by an elementary matrix. And that's why we use the word elementary there. Okay, so this leads to the following fact. Fact, if an elementary row operation is performed on an m by n matrix, you can actually do it even more generally. We'll say A. The resulting matrix can be written as E times A, where E is the elementary matrix. So E is the elementary matrix obtained from the m by m identity via the same operation. Okay, so that's a very nice fact, because matrix multiplication is better to deal with algebraically than describing row operations, which are kind of up in the air, right? And here's another fact. Sorry, that's not an if. So this is each elementary matrix E is invertible. Okay. The inverse of E is the elementary matrix of the same type that transforms E back into A, or that transforms E back into I, sorry. So a quick example. So E sub 1 was the matrix, was the elementary matrix 1, 0, 0, 0, 1, 0, minus 4, 0, 1. E sub 1 inverse is the elementary matrix 1, 0, 0, 0, 1, 0, 4, 0, 1. Okay. Now, why are we doing this? Okay, so there's two reasons. One, this gives us really nice examples of very simple matrices that are larger than 2 by 2s that have very simple inverses that we can just read off. So that's a nice thing, but that's not the main reason we do it. The main reason we do it is because this allows us to define an algorithm for computing A inverse. Okay. So I'm going to state a theorem, and then I'm going to say how that leads to an algorithm. And it leads to an algorithm because this tells us that we have finite steps associated with row reduction of a matrix. Each of the elementary matrices involved are invertible, so if the matrix itself is invertible, you'll be able to read it off from that process as long as you keep track of everything. Of course, if it's not invertible, you'll also be able to see it. Okay, so we'll see how this goes. So following theorem is nice. So if A, which is an n by n matrix, is invertible, maybe I shouldn't say if, because I'm going to state this as an if and only if statement. So A, which is an n by n matrix, is invertible if and only if A is row equivalent to the identity matrix I sub n by n. Okay, and in this case, any sequence of row operations that transforms A into I also transforms I into A inverse. This is an extremely important thing. So, first of all, we get our nice characterization of invertible. If it's row equivalent to the identity matrix. This is going to tell us a ton about what kind of matrices are invertible. So basically, if you go back to our chapter 1 stuff and what this means for the equation AX equals B, that matrix being row equivalent to the identity matrix is insanely nice for a number of reasons. That's going to tell you all kinds of things about its columns being linearly independent, whether or not you can ever get a pivot position occurring in every row or column, whether or not you could ever get this situation where in the augmented matrix for the system you get a bunch of zeros and then a non-zero entry at the end. All that stuff is going to be answered by this. Okay, and we're going to call that the invertible matrix theorem. But before that, this gives us an algorithm for computing A inverse. So this gives us an algorithm for computing A inverse of any size, if it exists. And what's nice is if you do this algorithm and the inverse doesn't exist, you will see it. Okay. So the idea here is algorithm 1. Set up the matrix that is a block matrix. It is A and I. So take whatever matrix is that you are trying to compute the inverse of and set it up so that you have the matrix A here and then I of the same size. So if we're looking at an A that's an n by n matrix, then A is an n by n matrix and the associated identity matrix is also n by n. Okay. 2. Row reduce it until you get the identity matrix on the left and something on the right. 3. The question mark is equal to A inverse. There's a little catch here, right? So there's a little catch. Maybe I should put an asterisk here. Okay. So this asterisk, what does this mean? The asterisk means if A is not invertible, this won't be possible. Well, what does that mean, right? What does that mean? Doesn't that kind of throw a wrench in the whole thing? No. The point is that you set up this matrix with A on the left and the identity matrix on the right. You do these row operations until you've put this matrix into reduced row echelon form. Okay, so put this matrix into reduced row echelon form. Maybe the reduced row echelon form is not the identity matrix. And if it's not, the problem with that is it's not invertible. So if you put this into reduced row echelon form and you don't have the identity matrix, so if you put this into reduced row echelon form and you don't have the identity matrix showing up on the left, then the matrix in question is not invertible. So you're going to get like a row of all zeros or something. You're going to get something that is not the identity matrix here, and there's no way it can be the identity matrix via row operations. And so if this isn't possible, then you know that A doesn't have an inverse. Okay, so let's see how this actually works. Okay. Someone said, doesn't that mean that all invertible n by n matrices are row equivalent? That's a really good question. So I'm not going to give a specific answer. I want you to think about that. That's a really good question to consider, whether or not any two invertible matrices are row equivalent. So think more about that, about whether or not that is the case. But that's a good observation. That's a good thing to think about. So let's do an example of this. So let's take the matrix A, which is 0, 1, 2, 1, 0, 3, and 4, minus 3, 8. Okay. All right, so I want to find A inverse. So find A inverse. That's what I'm trying to do. So what I set up is AI here. So if I actually write that out, what I have is on the left, I just copy A here. And on the right, I have the 3 by 3 identity. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so here's the matrix I have. Now I want to row reduce this thing sensibly. First thing I do is swap the first two rows. So maybe I swap the first two rows here. So 1, 0, 3, 0, 1, 0. And second row becomes 0, 1, 2, 1, 0, 0. And then 4 minus 3, 8, 0, 0, 1 here. Okay. So next I can zero out this entry. So I can zero out this entry and then also zero out this entry. I can kind of do that at the same time. So if I do 2 row replacements consecutively, so using row 1 to replace row 3 by minus 4, and then using row 2 to replace row 3 by 3, multiplication of 3. So I'm going to do 2 in a row. First one that I do is minus 4 times row 1 plus row 3, replacing row 3. And then I'm going to do 3 times row 2, replacing row 3. Oh, sorry. And when I do that, so my first row is unchanged, so 1, 0, 3, 0, 1, 0. I do the first, row 2 is unchanged too. 0, 1, 2, 1, 0, 0. And then what do I get in this line? So I'm going to get 0, 0 after I do each of these. So 0, 0, 2, 3, minus 4, and 1 is what I get. So now I can scale row 3 if I want. So 1/2 times row 3. What do I get there? This is, so first 2 rows are not changing. Third row is 0, 0, 1, 3/2, minus 2, 1/2. Okay, so now I want to use this one to zero out these things above, and then I'll be done. So I'm going to do that 2 operations here. So that's going to be so minus 2 times row 3 plus row 2 replacing row 2, and minus 3 times row 3 plus row 1 replacing row 1 here. So row 3 is unchanged, so this is 0, 0, 1, 3/2, minus 2, 1/2. So then in row 2, I get 0, oh, sorry, that's a 1. So 0, 1, 1 times minus 2 plus row 2, so that's 0. So this is minus 2 times 3 halves is minus 3 plus row 2, so that's minus 2. Minus 2 times minus 2 is 4 plus 1, so that's, 4 plus, wait a minute, minus 2 times, this is minus 2, so that's 4 plus row 2, so that should just be 4 then, because that's a 0. So that should be 4, and then lastly, minus 2 times 1 half is minus 1 plus 0, so that's minus 1. All right, and then lastly, I get 1, 0, 0, and then these remaining entries are minus 9 halves, and then 6 plus 1, that's 7, and then minus 3 halves. Okay, whoop, I'm a little bit off the page. Okay. Okay. All right, so then what is this? This is the identity matrix. So what should this be? This should be A inverse. So A inverse is minus 9 halves, 7, minus 3 halves, minus 2, 4, minus 1, 3 halves, minus 2, 1 half. Okay. So you can actually check if you wanted to. I'm not going to check this thing, but if you wanted to, you could actually check that A times A inverse is equal to the identity. So A times A inverse is actually equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. Right. Okay. So this is the process. Once you have seen this done once, this is how it always is. So what are you doing? You're just using row reduction here. It's just that in the case that A is invertible, when you use row reduction and put this into reduced row echelon form, what shows up here is the identity. Now, if what you ended up with here on the right wasn't the identity, say that this was 0, 0, 0, and then some stuff, then A is not invertible. That's what that means. Okay, because there's no sequence of row operations that would turn such a thing into the identity. Okay, so this is how it's done. So again, once you've seen it done this way, this is it. This is like the one example, basically. It can just get more or less tedious. So if you want to do this for a 4x4, process is exactly the same. It's just more tedious, right? And the larger the matrix gets, the more and more tedious it becomes. All right. Okay. And so that brings us to the invertible matrix theorem. So what is the idea here? The idea, an invertible matrix, A, is very nice. Okay, this is the idea. So the invertible matrix theorem tells you that there are a ridiculous amount of things that you get the second you know a matrix is invertible. Okay, and so to summarize this, I think it is best to have a gander at this long list. Okay, so let me make this. There we go. Now it's not as blurry. Okay, so here's the invertible matrix theorem. Okay, so let A be a square n by n matrix. Then the following statements are equivalent, T, F, A, E, and then I have a long list, A through L. We're going to add to this. I believe we get all the way up to like P or R here. Okay. So what I have here is the following. So 1, A is an invertible matrix. This is the important thing. Okay, this is, or I should say, this is the thing that we're saying all these other things are equivalent to. Okay, so note, A and B being equivalent is exactly that if and only if statement in the theorem that I had previously. Okay, so if A is an invertible matrix, that's true if and only if A is row equivalent to the n by n identity matrix. Okay, so it turns out that this is another list this is a further list of things that puts you in that exact same case of being row equivalent to the n by n identity matrix. Okay, so A has n pivot positions. The equation AX equals 0 has only the trivial solution. Well, the second you know that, that means the columns of A form a linearly independent set. The second you know that, you know by definition, or rather not by definition, but by that fact after we gave the definition of 1-to-1, that the linear transformation that has A as its standard matrix is 1-to-1. Then you also know that G, the equation AX equals B, has at least one solution for each B in Rn, which also tells you that the columns of A span Rn, which also tells you that the linear transformation that has A as its standard matrix is onto. So combining F and I tells you what? So before I move on, combining F and I says A is invertible if and only if the transformation that sends a vector x to ax, so this transformation t that sends a vector x to ax, is both 1-to-1 and onto. I know it's a little blurry here, yeah, here, there. So combining F and I says that if A is invertible, well, A is invertible if and only if the transformation T is both 1-to-1 and onto. That is one of the things that is said by this long list. Okay. So what else? It says there is an n by n matrix C such that CA is equal to I. That's being a left inverse. There's an n by n matrix D such that AD is equal to I. That's being a right inverse. And L, A transpose is an invertible matrix. That's this fact that we said previously. So these previous two theorems we said are A and B and L. Okay. And then all this other stuff is just tidying up all of these definitions that we've done over the course so far. Okay. So this list is basically what you should think of anytime I say A is invertible. So how to use this. So how to use this theorem. I'm going to take a picture of this later today and post it, and I'll name it in files the Invertible Matrix Theorem. There's going to be a part 2 that comes in a little bit at the end of chapter 3, so I'll add to it later. And the reason I'm going to do that is just it's a list that you should keep in your head, basically, anytime I say, here's an invertible matrix. So when you are presented with a situation in which you have an invertible matrix A you should think of that long list of properties that A satisfies. So that long list is the invertible matrix theorem. So what do I mean by that? There's many ways in how in which you could use this. So one is if you already have a matrix and you know it's invertible, then if you wanted to know any other facts about it, that list basically exhausts, what you know, or what, like, the most important things about that matrix. So that's one thing. Another thing is, say you wanted to know say in this example, right, you wanted to know something about this transformation being both one-to-one and onto. Then if you knew that this happens if and only if A is invertible, then the question you wanted to know about this transformation is translated into a question of knowing whether or not that matrix is invertible. And so then you solve the question of whether or not the matrix is invertible, and that answers this question about it being one-to-one and onto. Okay. So this is a very important theorem, and basically this theorem is a huge source of true-false questions. So there are going to be true-false questions asked for like the remainder of the course, and most of them can be boiled down to one of the parts of this theorem. Yeah, so someone said, so no non-square matrices can be both one-to-one and onto. Yeah, so that's one example. Yes, that is something you get out of it immediately. Since to even discuss being invertible in the first place, you have to be dealing with a square matrix, right? Yep, that is correct. Okay, and so that is a really that's a really nice fact. In fact, this gives you a notion of talking about invertibility of transformations in the sense of functions, right? And you might remember that finding inverses of functions was tricky business. You didn't always have them. Okay. So 2.4 deals with partition matrices. I'm not going to do that till the very end. So I will return to 2.4, but only very quickly. So section 2.4 will be skipped for now. The rest of chapter 2 is skipped forever because we're going to do it anyway in another form. So the rest of chapter 2 is always skipped because there's no point in doing it in chapter 2 when we're going to do it in chapter 4 in greater generality. So it's inefficient to do it in chapter 2. Okay, so anyway. And so that does it for chapter 2. And so we get into determinants. So I have a few minutes left, so I'm at least going to write the word determinant here. So chapter 3, determinants. Okay, so big question. How do I know if a matrix A that is a square matrix is invertible? And the answer is going to be compute the determinant of A and this is going to tell us straightforwardly, this is going to tell us. Second question. If A is an n by n matrix and n is at least 3, how do I compute determinant of A? Because right now I just have a silly AD minus BC description for the determinant. So the answer is the following definition that is very tricky. Actually, I don't think I quite have time to write the definition, so next time. But I will mention the following thing. There is a pretty hilarious book called The Theory of Determinants. It's like multiple volumes. It's thousands of pages long. So if you want to, or if you ever had the question like, well, maybe after you've seen this chapter, you'll have the question, where can I learn more about determinants? I think the author's name is Moyer. This was written in the, I don't know, like the 1890s or something, maybe the early 1900s. When the libraries at UMD are functioning, it is in the UMD library, because I've checked it out before. It is completely hilarious. Like I said, there's many volumes. It is nothing but an entire book of different types of determinants and their properties. So it's it's pretty interesting. Unfortunately, that's all I have time to say today. But on Wednesday, we'll start our full discussion of the determinant. We'll start and be done. We'll probably be done with determinants by the end of the week. And so we'll start on vector spaces and chapter 4 stuff next week. So I'm going to post like a schedule when you can expect your first exam and all of that soon. So I know I've been getting questions about when the exam is. Like I said, I'd shifted to a 2 midterm schedule, so you're going to have 2 midterms instead of 3. So your first exam is still a couple weeks off, but I'll let you all know. That way you'll know how it's going to go. I'll assign it some day. It'll probably be on a Friday, and you'll have a couple days to do it. So I'll post the midterm on Elms, and you'll have a couple days to do it like you do your homework, basically. Okay. So so chapter 2, we just did sections 1, 2, and 3. The rest of chapter 2 is skipped entirely, which is always how it's done for this course. That's not a decision I made. That's always how it's done in this course. Anyway, so I'm going to do office hours right now, so I will restart the stream. So if you have questions about homework, you can send them on. Like I said, the homework is due not tonight, but tomorrow night instead. So anyway, I will see you all maybe in office hours. Otherwise, I'll see you all on Wednesday. So that's it.